trisections. And we saw how they can be described by shadow diagrams, where each, a triple of data on the surface where each piece of the data is cut system and arcs. And so the one thing we didn't say is the main theorem, which is that every surface link XS admits a generalized G B C bridge trisection for some choice of parameters. Actually, the statement here is a little bit stronger, so maybe I'll rephrase this. The actual statement is that given a trisection T of X, we can put S in bridge trisected position with respect to the given trisection. So this is analogous to the fact that when we were talking about bridge trisections of surface links in S4, we put them in bridge trisected position with respect to the genus 0 trisection of S4. And the same is true given any trisection of any four manifold. And the proof is really quite similar. You can get a banded link description of the surface in the four manifold, which is a little bit more complicated because now you sort of have a handle body diagram with framed links and one handles and stuff. And then in there you have an unlink representing the cups and some bands representing the saddles. And you know that if you sort of resolve the one handles and the two handles, you'll get a connection of S1 crosses twos. And you know that if you resolve the bands along the cups, you'll get unlinked bounding the caps. And you want to basically put this thing in some sort of banded bridge position with respect to the generalized, or with respect to a Haggard, with respect to the given Haggard decomposition of the pieces, and on you go like that. So basically the same idea. One thing that's lacking here is a uniqueness statement. So so the question is, yeah. Maybe I'll be a little bit vague because I don't want to get into all the details, but does the obvious uniqueness statement, where here I guess I'm thinking up to perturbation and deperturbation, but fixing the trisection. So in other words, if I have a given trisection in my four manifold and I have two bridge trisected surfaces that happen to be isotopic surface links, is there a sequence of perturbations and deperturbations I can do to my generalized bridge trisections in order to relate these two generalized bridge trisections? And we didn't work that out. And the reason we didn't work that out is because if you remember how we proved uniqueness for for normal bridge trisections, is we leaned on this this uniqueness theorem for banded links, right? That said sort of any two banded links for the same surface can be related by cup and cap moves and band strings and band signs. And that theorem, that statement should be true in an arbitrary handle body. So this should just follow from general surf theory for 4-manifold, 2-manifold pairs, but it hasn't been written down or worked out anywhere. So if somebody wanted to learn some singularity theory, some surf theory, and write that down, then you basically get a uniqueness statement for generalized bridge trisections along the way, which would be nice to know about. And the other setting that hasn't really been explored along these lines is that of the properly embedded surfaces in form. So something I've been thinking about, getting ready to write up or finish writing up is the story for bridge trisections in that setting. And again, there, the uniqueness statement will have to wait on some sort of improvement of the literature in terms of surf theory for 4-manifold, 2-manifold pairs. In that case, in like the sort of real boundary. So surf theory. I think there'd be some interesting things to learn and do there. Okay, any questions? All right. Yeah, so maybe I'll just mention in passing that we also have a meridional stabilization for generalized bridge trisections. And so the idea is that, again, maybe I'll just kind of sketch a picture. But if we have our surface here, and I need to be a little bit careful. I didn't think about this before I came in here, but yeah, I need to be careful here. So I think I can do it. All right. So the idea is if we have here's a piece of our surface. I'll sort of draw it like this. So we're thinking of the alpha handlebar, the red handle body as being above. And then I'll draw what we also have is sort of two other colors worth of arcs coming out of these 2 points. And this is our shadow diagram. One thing we can do is we can stabilize our trisection surface. Maybe I should draw the picture. We can stabilize our trisection surface along the trivial arc, right? Which of course has this this membrane inside the handle body that gives the shadow. And if we do this, then this has the effect of giving us a new trisection surface where the genus has been increased. And it has the effect that our knotted surface no longer intersects that handle body because we sort of tubed around it. Okay. So in particular, and the yellow and the purple sort of now run through there. And so it essentially has the effect of lowering the bridge number by 1. And also, because there's a 4-dimensional picture going on here, you have to be careful because what you're really doing is this takes you from a B, C1, C2, G, K1, K2, K3, B, C1, C2, C3, generalized bridge trisection. And the output is to increase the genus by 1. Since I'm stabilizing along the 1 arc, I'm going to increase the union of the blue and the green by 1. So this goes to K1, K2 plus 1, K3. And then the bridge number decreases, and the corresponding number of disks also decreases by 1. I think I got those parameters right. So just like meridional stabilization with Hagar or generalized bridge splittings, we also have the same thing here. And the way that the curves show up on the new surfaces is we sort of get the obvious alpha curve coming from the membrane. And then we also get curves that do something like this. Oh, shoot, not working. Oh, sorry. I need to be a little bit careful here. Yes, I'm running into trouble. I guess these should be parallel. And they should be blue. Like this, and then right, and then the idea with now, how does that work? Purple arcs. How does the shadow diagram change? That's a good question. Yeah, actually, I don't think this is the right picture, actually. Sorry, I'm kind of doing this on the fly, but now I remember. The right picture, actually. So we have let's abbreviate this a little bit. We have a purple arc that say does something like that, and a yellow arc that does something like that. Actually, the right thing to do here is to take a purple arc that looks like that. I guess, sorry, that should be blue. Should have stuck with my decision to not try to do this. And the arc, the shadow arc then persists, say, along the back of this guy and out like that. And this shadow arc, say, persists maybe along the front of this guy and then back out along that. Okay, so we lose, if you notice what happens is we lose a yellow arc, a red arc, and a purple arc. And we get some sort of diagram that looks like this. And it's not too hard to tell that even though these don't exactly look parallel, the blue and the green curves that we get actually do correspond to sort of a common blue-green curve in the overlying diagram. So let's see. I guess, was this in our paper, Dave? We did this for the sponge trouble. I don't think it was in the paper though. So I think in the paper with Dave, we worked this out.
Oh yeah,
Yeah, right.
Whether it was in the paper or not, I forget, but we worked it out. I know we worked it out.
I think we worked this out for this. Or did we just spin the one bridge thing?
I can't remember.
Where would this be? This must be somewhere.
It's
Okay, well,
on a
it's
piece of
an
paper.
exercise. So in the paper with Alex in PNAS where we do the generalized bridge trisections, we describe this meridianal stabilization operation in detail, and possibly somewhere it has appeared how to do this for like this sort of nice picture of a sponge rubber. But it's a good exercise, one I've done probably a dozen times. for the sponge rubber. So in particular, we can always do meridianal stabilizations to decrease the values of the CI, provided they're not already 1. Because if you think about what this really sort of corresponds to, is it corresponds to taking the yellow and purple unlink and attaching a band. And the band gets attached in such a way, and you can kind of see that band. The band runs over the handle here. The band gets attached in such a way that if you choose your arc right, it will be a banding of an unlink to a new unlink. And so that's what you need in order to still have a bridge trisection. But if you only had, if this was part of the same component, say, you'd be in a little bit of trouble because you'd be sort of self-banding you'd have your trivial disk, that's purple and yellow, and you'd self-band it so there will be an annulus. But the corollary, I'll say the more general corollary, then I'll write the more specific one. The corollary is that we can perform meridianal stabilizations on a generalized bridge trisection until all of these CI are 1. Sorry, I guess maybe until all the CI are the number of components in the surface length. But so in particular, every 2 knot admits a G, K, I guess it can be balanced, GK 1, 1 generalized bridge trisection. Because if it's a connected surface, then we can do these meridional stabilizations to reduce the CIs until they're all 1. And then by Euler characteristic reasons, a 2 knot, which has 1 patch in each system, has to be sort of the, you know, the nicest picture of the sphere. This guy. Abstractly, that's what it looks like at that point. For higher genus surface knots, you can get this down to like, you know, whatever it is, 1 Euler character, negative 1 minus Euler characteristic or something. It must be that. No, that's not right at all. It's more complicated. Anyway, it's the Euler characteristic. See, it wouldn't be a lecture if I didn't mess up an Euler characteristic. Anyway, so for example, the torus, you know these numbers from the classical case. The torus admits a 3, 1, and then genus 2 is that. I guess Klein bottles 2, 1, something in there. These guys. So there's some linear formula. And then the corollary to this is that every 2 knot. So now we're thinking of pairs. XS, where S is a sphere, is described by a doubly pointed trisection diagram. Okay. And we saw an example of this. I think I'm actually going to revisit the example at the end of last class. Oh, there's a good exercise here. Since Dave taught you about relative trisections. Did you say anything about 2 knot complements?
No.
Okay. Show that the exterior of a 1 patch bridge trisected 2 knot is naturally relatively trisected. This is kind of strange words I'm using this, but the idea is that if you put your 2 knot in this 1 patch position where you've made all of the C's 1, so each sector contains 1 patch, and you remove a neighborhood of it, then the exterior of the bridge trisected sphere in the trisected format is naturally a relative trisection with an annular open book decomposition on the boundary. So it's pretty cool. It doesn't work. And then the next exercise is, why doesn't this work for other surfaces, and find a way to fix it. I'm going to put that down because I think it's a good problem. Well, I guess it's been sort of been addressed by Maggie and Young Long, but yeah, maybe it's still a good thing to think about. For surfaces that are not a 2-sphere, and how could this be fixed? So Maggie and someone do give a way of getting a relative trisection for a surface not exterior from a generalized bridge trisection. But this remains a sticky area, I think. Worth further thought. Okay. I think this is kind of what I wanted to say about the general theory of generalized bridge trisections. Does anybody have any questions? Or does anybody know of anything that I should be saying that I haven't? So probably then for the last half hour, I'll talk about just some examples of bridge trisecting surfaces in CP2, in the notes, what I at least outlined that I would do is to show how to take branched covers and get some interesting trisections and complex surfaces out of it. Although I don't know what we're gonna get a chance to do. Okay, for the sake of time, I think I'm not going to recreate the CP1 example that I did from last time. I'll skip to the conic. So here's an example of a generalized bridge trisection of a surface. So this is a trisection diagram for CP2 if we think, so I'll go ahead and draw it here. If we think of this square as giving us the torus, I need to get a little bit careful here. If we cut this guy open, then we get this picture. So this is a little bit of an easier way to draw things. And then the surface that I'd like to describe is going to have, it's going to have a doubly pointed trisection diagram given by these two dots. And this is enough data to encode the surface because there's essentially a unique way to connect these dots with arcs in the complement of the given color. So for example, I could connect with a blue arc. You know that test where you have to read words and they're written in their own color? Okay, I'm going to try to do that. So I connect these in a blue arc here. I could also connect these with a red arc in the exact same way, but I'm gonna opt for something that's a little bit more symmetric, which is to make my red arc hit only the blue curves. My blue arc hits only the green curves, and then my green arc will hit only the red curves. And so again, these sort of off-color colors were not necessary to be drawn, but actually, with what I'm going to do, it will be important. So this triangle in the top right is this triangle, so I get a dot here. And then to get to this triangle, so by triangles I mean this and this. So the way I've drawn the green curve is to cut this into a hexagon and two triangles. And so to get from this triangle to this one, I can cross the red guy into the hexagonal region, and then I can cross the green guy. So I claim that my second dot belongs there. This is always very difficult for me to work out where how this picture maps onto this one, but I think this is right. I mean, if it's not right, we'll surely run into a problem when we try to draw these arcs. So now the red arc hits the blue curve twice and misses everything else. So it ought to look something like this. The purple curve hits the green guy twice. Connects those up. And the green arc hits the red guy twice. And they have this triple point up here. You can see why we draw it this way. So why am I doing this? Well, the reason I want to do this is because I want to convince you what this surface looks like from a handle body perspective. So because this trisection diagram is standardized in the way that I discussed a few lectures back, in that the blue handle body is the obvious sort of outside of the blue handle body is obviously embedded in the blackboard 3 space. We can convert this to a handle body diagram. So if we sort of think of the green curve as giving us a surface frame 2 handle, what we get is this. Something like that. And the framing that comes along with it is +1. Okay. So this describes the ambient 4 manifold. Now, how do we describe the surface? Well, this is not something I've given you guys the right background for, but the idea is that Morse function on the 4-manifold induces a handle decomposition of the knotted surface in which we have some cups, some bands, some saddles, and some caps. Now, in this case, if you think back to the combinatorics of how the handles correspond with pieces of the bridge trisection, the cups come from the union of the red and blue arcs. Right? That's an unlink. In this case, it's an unknot. So we have a single cup. And then if you think about where the bands come from, well, at least the number of them is supposed to be B minus C2. So that means we're going to have 1 minus 1 equals 0 saddles, and then we'll have 1 cap. So this 2-knot is actually just built as a cup and a cap inside CP2, in the same way that CP1 was. So that's a little bit interesting. So there are actually, so I guess there's actually 3, probably exactly 3 2-knots. Yeah, we know this. 3 2-knots in CP2 that can be built without saddles relative to sort of the Stanley Morse function. Okay, but anyway, so let's see how that works. So let's take our blue arc. Now remember, we really want to think of this blue arc as living in the blue handlebar. So I'm going to push it out off of the surface a little bit. That's why it's going to go over the green. The green guy, it's also going to go over I guess it goes over both of those like that. It kind of sits over everything. I worried about this for a little while because we also usually think of pushing the green curve into the beta handle body.
Well, it's really going to the gamma handle body.
No, to get a diagram, you usually push your gamma link into the beta handle body. But what I realized is you don't actually have, I mean, that's the right way. Well, I think I presented sort of both views. The point is you don't have to move the gamma curve.
Right.
And if you don't move it, it avoids this issue of does it go above the beta arc or vice versa. So I think the gamma curve should stay on the surface and the arcs can push off. And then we should draw this guy, which kind of does this. And if we redraw this, the picture we get is this is +1 frames. I can drag my points around sort of however I want. So maybe I'll do this, and then this goes something like this. Okay, so this is kind of interesting. So the purple and the orange represent the boundary of my cup. And where is the cup? Well, this picture is being drawn in the boundary of a 0 cell, 4-dimensional 0 cell. So this is it's an unknot. So it bounds a canonical cup into the 0 cell. And we know there's no, so now where does the cap sit? Well, the cap shows up after we resolve this 2-handle. And so one way we can think about this is we can think of the effect of attaching this this 2-handle is, well, one way to think of it is we blow down that curve, right? The effect, this is a Dane surgery from S3 to S3. Another way to think of it is we could slide the sort of the attaching region of our cup as it moves up past the 2-handle, we sort of slide it off. So we could slide it twice this way. And the effect is that, well, if we blow this down, it adds, oh, I had it right before, I think. Actually, I might have done it wrong in my notes. Thanks, Jason. I had it right in my notes. The effect of blowing this down is to add 2 negative twists to this thing. But since they already had a positive twist, the 2 negative twist turns it into this. So this is the effect of sort of blowing down along that curve on the sort of equator of our 2-knot. And the fact that it is now another unknot in now our higher version of S3 means we can cap it off in a canonical. Okay. So, but this was a very special thing, right? I mean, to consider sort of interesting 2-knots in CP2, or with at least respect to this handle decomposition, you want to consider things that link this handle in an interesting way so that they're an unknot, and that when you blow them down, adding this full negative twist, they're again an unknot. And so I think in the paper with Alex, we proved that you can do it this way, and then the example from last time, as you can probably guess, what does CP1 look like from this view? Well, it just looks like this. And then, yeah. This is a picture of CP1. This is a picture of the degree 2 curve of the conic in CP2. Okay. And now, I mean, you kind of have, I think, at least the basics for what you would need to consider sort of more complicated handle body description of knotted surfaces in form manifolds. You could have more complicated form manifold descriptions, and then you could also have bands floating around in the picture.
Question.
Yes.
So if you fix a trisection diagram of form manifold and you ask the question, how many two knots could be described by it?
As like doubly pointed
Yeah.
with respect to that exact diagram.
Yeah. Then you've got a finite number of regions.
Yeah.
Number of regions, choose 2 basically,
Yeah.
and those will all be distinct. Or,
Well,
or that's an upper bound.
Some of them might not be bridge trisections. Because if you put down 2 points, so this gets back to that trefoil example I mentioned, right? Where if, say your diagram happened to look like this. Right? Pretend this is a trisection. I could add a green curve. It's a trisection diagram for CP2, right? Well, if I put my points right here, then the knot described just in terms of the red-blue part is not an unknot, it's a trefoil. So there's always this condition to check, which is that you should be getting an unknot. And for doubly pointed diagrams, there's a nice way to characterize this, which is that you should be able to draw, or you should be able to do slides, you want a fixed diagram. So like in this diagram, I mentioned that the orange arc can be slid to coincide with the purple one. That's exactly the condition that orange and purple together give an unknot. Okay. Because just because of what a one bridge splitting of an unknot looks like, they have the two membranes have the same shadow.
But it's a finite number though.
So you're right, it's a finite number given a fixed diagram, but
Yeah.
if you start isotoping curves,
Right.
it's not. But yeah, but it is a finite number, and you could do the check. Okay. Oh yeah, so there's a nice exercise that comes on the heels of this. So I've sort of exhausted the easy doubly pointed examples in this diagram, but actually you should do this, what you just mentioned, in S2 cross S2. Because there's a handful of interesting knots that admit doubly pointed diagrams with respect to that. So how did I write this? Oh yeah. Discover the doubly pointed trisection diagrams for the two knots in S2 cross S2 in the classes 1, 0, 0, 1, and say 1 plus or minus 1 in H2. So sphere across a point, point across a sphere, and then the two sort of diagonal, the diagonal on the off diagonal side. And you can use what I just sort of showed you here to pass to a handle body diagram where you can really understand, oh, I see exactly what this thing is to sphere across a point because its equator is on meridian to one of my 2 points or something. Very clear. Okay, what to do now? Let's see, I guess we can try to work through a branch cover example in 15 minutes. Okay, I'm gonna try to do this, and there's just a good chance that we're gonna stop for some percentage of the way through. There's a good chance we will complete some portion of this. Okay. Especially because it's going to be complicated. So I guess I should at least show you Peter's excellent pictures of complex curves. That kind of got our project kicked off. So this is what Peter discovered. He discovered that if you take the picture I gave you for CP1 yesterday and you tile the torus with it, so let's see, how do I convention this? So it's going to do it like this. So here's my blue arcs. Here's my red arcs. You can see now that very clearly what I've described now is let's see, how many arcs are there? Well, there's 9, I guess. So this is a 9 bridge splitting of a 3-component unlinked. So this is going to be a 9-3 bridge trisection. The green curve goes like this, and the green arcs go like. Okay, so this is pretty cool. So we have 18 bridge points. We have 9 arcs of each color, and you sort of saw as I was drawing it that red and blue together given unlinked, and it's not too hard by symmetry to see that the other one's given unlinked. Although sort of like the red or the yellow and orange ones, they actually, if you drew them in space, they look like they were giving like a 3-3 torus link. But because they're in the green-blue handle body, you untwist it and it's magically magic. So this is a 9-3 bridge trisection for the cubic curve. The degree 3 curve in CP2. And you can see how, in general, you can get the degree D curve. You just take, d² copies of this sort of picture and tile it up. Okay. And so the next observation we had is that this, and by the way, the cubic is a torus. It's a torus. And it's fundamental group, so maybe I'll just mention that if you take CP2 and you remove a neighborhood of a degree D curve and you take the fundamental group, what you get is the cyclic group, or D. Yeah. So there are algebraic conditions on B and C, like we mentioned in the S3 case, coming from like the meridional rank. Well, in this case, the meridional rank is 1. So it's natural to ask if this thing admits a bridge trisection that's 1 patch. In other words, can we reduce this to a 3-1 bridge trisection? Or in general, a B1 bridge trisection, depending on the Euler characteristic of the degree D curve. And it turns out that you can, because, well, if you think about this unlink, the vertical unlink, these yellow arcs connecting them represent sort of trivial, well, if you remember how we destabilize in a shadow diagram, this is exactly what we look for. We look for a clean, say, gamma arc that connects 2 distinct components of our red and blue arcs, such that its interiors disjoint. And if that's the case, then we can sort of delete it and resolve across here. And we have lots of clean arcs in this picture. And the question is sort of, do we have enough? Because to do this, we need to find 2 clean yellow arcs, 2 clean blue arcs, or purple arcs, and 2 clean orange arcs. So a total of 60 stabilizations. Well, it turns out that this hexagon here gives us a destabilization of one of each color. And now I need to be careful to pick the right hexagons. Oh, I only need 2. Okay, good. So I could do, let's see, I'll stick with what I was saying. I can pick this yellow one, this purple one, and this orange one. And it shouldn't be too hard to convince yourself that these 3 destabilizations are going to be independent. So I can basically do them all simultaneously. This is essentially a balanced deperturbation of the bridge trisected surface. It will lower B by 3 and each of the C's by 1. And then I can do the same thing with this one. And it turns out that you can just automatically see that you can find enough hexagons in any of these pictures to always get down to a one patch thing. Okay, so what does that look like? Well, let's see, which points? I'll try to do this so that it makes sense to you. Okay, so which points are not affected by this? Well, it's this one, this one, this one, this one, this one, this one, which is 6, which is how many we should have. All the other bridge points sort of disappear. So when I sort of crush this guy, and I crush this guy, and I crush this guy, then this purple one ends up just going straight across like that. And these purple guys survive. Similarly, let's see. This guy survives. So this orange guy comes out to here. I guess that survives. Probably another one over here of the same sort. That's easy. I guess there's probably a reflected yellow one of the same sort. Okay. So we're missing one. What are we missing? A yellow and an orange. So what does this yellow guy go? Well, let's say we destabilize here. Here and here, which means this yellow one. Oh no, sorry. This yellow one. So where does it go? It goes here, but when we destabilize along this purple one, it joins this guy. When we destabilize along this orange one, it joins this guy. So it ends up going off the midpoint of the page and ending up back there. And then the orange guy does the same thing. And so this ends up being our shadow diagram for the same cubic torus, except now in this efficient. We call this efficient if it has sort of minimal patch number. Efficient bridge trisection. All right, any questions about that? Because it's probably better that I make sure that what I just did makes sense. Is it okay? Or is it too, maybe a little fast? Okay. Yeah, that's okay. Maybe I'll draw some like more stepwise pictures. So for example, the first thing maybe you do is that you destabilize along this yellow arc here, which locally looks like this. And what does that look like? Well, it looks like, oh, that can't be right. Locally looks like this. Right, so it gets rid of the yellow arc and it sort of merges the purple and the orange. In fact, in a sense, this is giving you a half, this corresponds to a half twisted band. So let's see, which one do we usually think of being above? I guess purple's above. So if we think of this as sort of purple being above and orange being below, orange is below, purple is above, what we sort of see is a band that sort of looks like this. And this band intersects the, maybe I should make the band green. The band intersects the surface in its core, and it's vertical. The reason it looks half twisted is because my arcs are going in the wrong way, but it really is kind of like a vertical band. And so doing this destabilization sort of is like thinking of this gamma arc as a saddle and canceling or resolving this band, which because we have an unknot on each end, a distinct unknot on each end, it just gives us a new unknot. Actually, yeah, so there's like, all right. And then, so essentially, one way to think about what you did here is you did this sequentially 6 times. The hexagons just help you to see that I can do this simultaneously on all of these because they're sort of disparate enough that they won't. The main thing you need to be careful of, so the thing you need to be careful of is when I resolve this one, I take this component and this component, I make them one. So I better not then say choose this one, because that is now a self-banding of the same component in light of that. So that's why I chose you need one of these bands in this column that parallels these two. And so the same thing. So basically these asterisks are arranged so that there's no 2 in the same like column, row, or off column, but they are 1 in 2 different columns, something like that. Yeah, so like, so this purple row has an asterisk, this purple row has an asterisk, but this one doesn't. This yellow column has an asterisk, as does this one, but this one doesn't. And then, should I put 2 in the same? Did I get it wrong? What do my orange rows look like? I think I might have put 2 in the same orange row. Yeah, good. Okay, so let's say I put 2 in this row. So I was being sloppy. And if I have
So your picture on the right looks good.
yeah, but I sort of black boxed going in. Well,
Because I mean, you should be able to, if you do it wrong on the left,
oh,
doesn't that mean you're going to get it immersed, like self-crossings of arcs on the right?
sorry, maybe I'm picking the wrong diagonal for orange.
Yeah, you are.
Yeah,
Go the other way.
let's think about this, because the orange connect, yeah, sorry, I did it wrong for purple. The orange bands go between the purple-yellow horizontal endings. So what I should have said is I have an orange here and an orange here. It's the purples I did wrong, because the purples go between the orange-yellow diagonal ones. So I have a purple here and purple here. And the triple points of what I just drew are those. Coincidentally. Okay. All right, so we're totally out of time, but I'll just say what I would do next. Next, I would show how you can sort of take the branched cover of this surface by cutting this diagram open, taking 3 copies of it, and the 3-fold branch cover. So to take a branch cover, you need an epimorphism of the surface link exterior onto a cyclic group. And so if we are at Z3, we need to be doing a 3-fold cover. And so there's a way to sort of cut this open, take 3 copies, lift the curves, lift the arcs, and you get something that looks like this, where it's essentially, you throw away some curves, that's why it's not totally symmetric. But in this example, which I guess is now an exercise, when you take the 3-fold cover, you get CP2 blown up 6 times. And the diagram you get seems to not be stabilized or reducible. So this would be a good thing to try to investigate as to whether it's stable or reducible. The other thing I'll say, I can say this by just showing you guys the picture, but when you draw this diagram, the pairs of curves, the alpha, beta, gamma curves in pairs are really nice. So I drew the alpha, beta curves here. And what you see is that they're almost standard. Like these guys are dual, 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 these guys are dual. All you need to do is do a few slides of red 1, 2, 3, and 4 over red 5, 6, and 7, and they come clean. And the same, it's symmetric. So same thing with the blues. You need to slide the blue. Maybe the numbering's actually changed, but 4 of the blue curves over 3 other of the blue curves to make them dual green, and same thing with green. So these seem to be really interesting examples of trisection diagrams that I think warrant some understanding, like what's going on with the Dane twists, or the, what you would call it, the surface automorphisms as you go around in a circle like we were talking about. So that's all. You guys, good attendance. Good attendance this semester. And no final.